Hello everyone, welcome guys. As you can see on the board, I have written some terms, coordination number and all those things. In previous videos we have done examples, we have done derivation and theory part. Now we are going to switch for 1 mark questions which are generally asked for entrance exams, and for that you need this table. And one more concept is there, as in video 5th or 3rd or 4th video I explained that there are 3-dimensional and 2-dimensional arrangement of atoms. In that, you can go through that video. In that, we have seen that there are octahedral holes and tetrahedral holes. If you have seen those videos, then and then only you will understand this concept. There are octahedral holes and tetrahedral holes based on the arrangement of the atoms AA type or AB type. Now, octahedral holes and tetrahedral holes, both the holes are present in AB type of 3-dimensional arrangement of atoms. Now, in this table, you can see that we are having R plus upon R minus limiting value. What is that limiting value and what is the term? As we will solve the examples, you will try to understand this table based on those examples. But what you have to do is, you have to compulsory remember this whole table, and based on those on this table only, there are 2 questions compulsory asked in entrance exams. We will try to solve that example, which will help you to understand it more properly. First, predict the coordination number. We are asked what? Coordination number. Predict the coordination number of cyanide plus iron, cesium plus iron. Predict the coordination number of cesium plus iron and structure of CSCl. Here we are having the structure of CSCl. If RCS plus is equal to 1.69 Armstrong, which is given to us, and RCl minus is equal to 1.81 Armstrong, which is also provided with us. So first what we'll do is, we'll try to find out the coordination or limiting value. For finding out the limiting value, we will just do what? R plus upon R minus. So 1.69 divided by 1.81. And this simple division will give us an answer, and that answer is 0.9337. So our answer is greater than 0.378. Our answer is greater than 0.378. That means the coordination number is 8 and the structure is cubic structure. This you can write down in the statement. Okay, what you can write down? The answer is greater than 0.372. This table is not provided to you in exams. You have to by heart this table. So based on these values, you can then identify whether it is which structure, octahedral, tetrahedral or planar triangular. Whichever the geometry, it is dependent upon the coordination number, and we get the coordination number depending upon the values of R plus and R minus, which are always provided to us. You don't have to learn that. Okay, we will now try to solve next example. Predict the coordination number of Na plus iron and structure of NaCl crystal if radius is given to us, radius of sodium ion Rna plus is given to us, and RCl minus is 1.81, which we were knowing previously. Rna plus is equal to 0.95 Armstrong. Now remember, the units are all same. RCl minus is equal to 1.81 Armstrong. Both are in Armstrongs. Armstrong is what? Armstrong is equal to 1 Armstrong is equal to 10 raised to minus 10 meters. This is the conversion. If you are provided with different units, you can, with the help of this conversion, you can convert the units in same units. Different units will not give you the exact answer. So we will what? Plus upon minus. So 0.95 divided by 1.81. On dividing these two with the help of log, we will get the answer as 0.5248. Now our answer lies between 0.414 to 0.732. That means what? The coordination number is 6 of NaCl and the geometry is octahedral geometry. So in this way we can find out the coordination number and geometry based on the table, which should be learned by you compulsory. Now there is one more 1 mark example or MCQ based example in which we need to understand one conversion. Here we are having octahedral voids and tetrahedral voids. In octahedral voids, the ratio is provided to us for metal and ligand ratio. Now in previous lectures also I had explained what is ligand. Now here, what is the ratio for octahedral voids? It is 1:1 ratio. 1 ratio is for metal and 1 is for non-metal. As you will see the example, you will understand it more clearly. And for tetrahedral voids, this is for octahedral voids. For tetrahedral voids, ratio is 2:1, where 2 is for metals and 1 is for non-metals. Directly we will move for an example which will help you to understand. Zinc sulfide crystallizes with zinc ions occupying half of the tetrahedral holes in a closest packed array of sulfide ions. What is the formula of zinc sulfide? What is the formula of zinc sulfide? Now they have told us that the tetrahedral voids are there and metal ion, that is zinc. Zinc ion is occupying half of the tetrahedral voids, and they have not explained us anything about the non-metal. So we will keep it as it is. These two will get cancelled and we will get the ratio as what? 1:1. So the formula for zinc sulfide is Zn was 1 and sulfur atom 1. This will tell us the number of atoms present in that molecule. This is one way to solve. Second example, aluminium oxide crystallizes with aluminium ions in 2/3 of the octahedral holes, and 1/3 octahedral holes remain vacant in a closest packed array of oxide ions. What is the formula of aluminium oxide? Now, what is the example? That aluminium oxide crystallizes with aluminium ions in 2/3 of the octahedral holes. Means 2/3 of the octahedral holes are occupied. Aluminium is metal, so 2/3 of the octahedral voids. Octahedral has ratio as 1:1. So 2/3 into 1 as to 1. Now next, what they have explained is that 1/3 part is vacant. So we don't need that 1/3 part. It is just given you to confuse. So occupied part only we are going to consider. 2/3 part of the metal part is occupied and remaining is vacant. So we will get what? 2/3 as to 1. These 3 will go for multiplication and we will get the ratio as 2:3. That means what? Aluminium is 2 and atoms of oxygen are 3. In this way we will get the formula for aluminium oxide, that is Al2O3. This is one example, and there are many different kinds of examples which you can solve based on the MCQs which you have, or you can try to solve the examples. If you have any doubts, you can comment it in the section and we'll discuss that part, or we'll make a video over it and try to solve your doubts. Now next, we are done with the examples. 1 mark examples are done. Now we will be moving for theory part, where we are going to see the defects present in that solid. There are many solids. You can't have an ideal solid, never. Ideal solid does not exist. There are always some defects present in that solid, and defects which are given to you are of two types: line defect and point defect. Those defects we are going to see ahead. So before moving for defects, I will clean the board and try to make a flow chart which will help you to understand the differentiation part more easily. There are MCQs and 1 mark questions asked for this. Defects are of two types: point defect and line defect. point defect and line defect. This line defect is divided in three parts: impurity defect, interstitial defect, and vacancy defect. Okay, impurity defect, interstitial defect, and vacancy defect, these are the defects. And impurity defect is again subdivided into two parts, that is substitution defect and interstitial impurity defect. Here also we are having interstitial defect. These defects change the, why are we studying defects, that I am answering you. These defects change the properties of solids and they give you an exceptional property. If I am going for, I'll give you an example, I am having gold. When we are having a lump of gold that appears to be yellow colored, but when we go on reducing its particle size from macrometer to micrometer, means when we are moving for 10 raised to minus 6 meters, 10 raised to minus 9 meters and 10 raised to minus 12 meters, in those range the color of that gold changes, and that change in color is due to the change in its particle size and change in its the excitation of the electrons due to it. We observe color because there is excitation of electrons. If excitation of electrons does not take place, that solid will appear to be in white in color. Okay, if the electrons are not present, then also it will appear to be white. And if there are electrons present but they are not going excitation, then we will have that permanent white color for those solids. Many questions are asked why we observe different kinds of colors for dye and other metal ions. That will come under C2 part, where we will be seeing D and F block elements. During D and F block elements and then coordination compounds, in these parts we will see how we can see the different colors for D block elements. Okay, so in defects there are point defect and line defect. In line defect there are three parts: vacancy defect, then interstitial defect, and impurity defect. Vacancy defect is also known as Schottky defect, where Schottky defect means what? If I am having ionic compound, this is the ionic compound, right? In Schottky defect, what happens is cation and anion are absent in that crystal. Means when we are trying to make salt and when we try to crystallize it, what will happen? In Schottky defect, one cation and one anion will be lost. They will be completely lost from the crystal. They won't be present anywhere. That means what? The density of that crystal unit decreases. Okay. Now that is what for Schottky defect, which is also known as vacancy. Vacancy means what? रिकामी जागा. Vacant means रिकामी जागा. म्हणजे ती जागा रिकामी राहिली. Next, interstitial means what? If I am sitting in a classroom where I have asked to sit on the same bench, two students are allowed to sit on a bench, and we generally, when we were kids, we used to do that. We used to settle down with our friends, and 3 people on a bench or 4 people on a bench, we used to sit in the way. In the similar fashion, what happens is when the crystals are getting formed, few metal ions or few cations, anions, leave their places and occupy the interstitial positions. Means what? If I am having NaCl and NaCl over here, what will happen? The crystal is in huge form, few parts which are present, few atoms which are present in different positions will try to occupy the position, interstitial position, म्हणजे मधली जागा ते ऑक्युपाय करण्याचा प्रयत्न करतात. They try to occupy the interstitial positions. मधल्या जागा ऑक्युपाय केल्या जातात. ते क्रिस्टल मध्येच असतात. मुलं क्लासरूम सोडून जातात का? नाही. बेंच फक्त काय झाले, मुलांची संख्या बदललेली नाही. क्लासरूम मध्ये मुलं जेवढी होती तेवढीच आहेत, फक्त त्यांनी बेंच चेंज केले. हे होतं कशात? इंटरस्टेशल पोझिशन मध्ये, बरोबर. मधल्या जागेवर ते येऊन बसतात. आणि वॅकन्सी डिफेक्ट मध्ये काय होतं? रिसेस झाली, लेक्चर नवीन सुरू होणार आहे, रिसेस मधून ते क्लासमध्ये आलेच नाही, मीन्स दे बंक द लेक्चर. सो बंक केलं म्हणजे काय? जी आधी क्लास मधली संख्या होती ती संख्या कमी झाली, द नंबर हॅज चेंज, द डेन्सिटी हॅज डिक्रीज. सो in Schottky defect density decreases, in interstitial defect density of the crystal remains same, there is no change in the density, but the position of the atoms changes. They can be cation also and anion also. Generally they are the atoms having smaller size which replace or which dislocate from their position. Next is what? Impurity defect. This defect is very important because of that defect we are having stainless steel. Now when we try to make stainless steel, we add nickel, cobalt and carbon, small amount of carbon, few percent, that is 0.3% or 0.03% of carbon. Depending upon the carbon content, the strength of that ion changes. So what is the substitution defect? We are adding, if these are atoms of iron present in a crystal, we are adding nickel and cobalt, then what will happen? These nickel and cobalt have approximately the same atomic size of iron, approximately same atomic size of iron, so they will easily replace the iron atoms. This is known as what? Substitution defect. When we are seeing football game, we have a substitution of player. Means what? One player is, number of players does not change, the number of players remains same. What happened is the player substitutes itself, means they are having change in number, like 66 number goes down and 9 numbers comes up in the ground. That means what? It is a substitution. Number of students does not change or number of players does not change. That is known as what? Substitution impurity defect. And next we are adding carbon atoms. Those carbon atoms are like interstitial impurity. Interstitial defect means what? Here there are atoms and here you can see the void spaces. In those void spaces, few carbon atoms get substituted and there we get interstitial impurity defect. In this way, these are the parts of defects which we have seen, and these defects are very important. Based on those defects, many twisted questions are asked for MCQ. Now moving ahead, we will go for band theory. In band theory, the basic part is what? We are able to see the conductance in metal ions. Like if I will take magnesium, magnesium is good conductor of heat and electricity. Magnesium has 12 electrons, which we can write it as 1s2, 2s2, 2p6 and 3s2, K, L and M shell. M shell has capacity of 8 electrons, means there will be empty 3p shell. Right? This empty 3p shell helps for the conduction of current. How? That we will see. Here the shells are not taking part in any kind of change because these are inert shells. Only outermost shell takes part under bonding, which is known as valence shell, and electrons present in that valence shell are known as valence electrons. Means we are having valence electrons as 2 valence electrons present over here. So we can, in band theory, this 3s2 is known as valence band and 3p0 will be known as conduction band, which is empty. Now when we apply potential difference plus and minus, when we apply potential difference through the cable, electrons from valence band move to conduction band, and this excitation or this movement of electrons lead to the transfer of current with the help of electrons. Electrons leave their position and they go to the next part, that is known as what? Transfer of electrons, which result into current. Now the gap is very less, that's why there is easy transfer of electrons between valence band and conduction band in metals. Now if you will see semiconductors, in semiconductors there is a gap present between these two semiconductors. Now there are two types of semiconductors, natural semiconductors and artificial semiconductors. Natural semiconductors means what? With increase in temperature, conductivity increases. Those are semiconductors. With increase in temperature, conductivity increases. With decreasing temperature, at lower temperature, they act as insulators also. Okay. So with increase in temperature, what happens? The band gap decreases and electrons can get excited. Like I can show you. With increase in temperature, what happens is the band gap gets reduced. Conduction band and valence band overlap on each other. So at higher temperature, we can carry current through semiconductors. But it is not possible. Why? Because semiconductors are generally used in electrical appliances. Right? So the semiconductors which we are using, those semiconductors are widely used in electrical appliances. Because of the semiconductors, we are able to reduce the size of the mobile. At smaller size, we can have higher efficiency. That is the effect of semiconductors. Okay, so these semiconductors should be operable at room temperature. They should be operational at room temperature. So to operate them at room temperature, we make artificial semiconductors. And artificial semiconductors are of two types: N-type semiconductor and P-type semiconductor. N-type semiconductor means what? We add impurities having large number of electrons. Like in this semiconductor, we can add fluorine gas. That fluorine gas occupy interstitial positions. Interstitial means what? Madल्या जागा तो fluorine atom occupy करतो. And as fluorine is having 7 free electrons, it is having 7 free electrons. That's why it is known as N-type semiconductor. And these 7 free electrons give us conduction. That is known as what? N-type semiconductor. Okay. Next we are having P-type semiconductor, where we can add boron gas or any other impurity which is having less number of electrons. Electron number must be at the max 3. Above that, we can't use those semiconductors. So the electrons should be less than 3 and should have large void spaces. Means what? For an impurity like boron, which is having only 3 electrons present in its outermost shell, and it is having 5 holes. So those holes are available for the electrons to excite. This is what? P-type semiconductor, and this is the energy level for N-type semiconductor. This is energy level for P-type semiconductor. P-type semiconductor has holes present in them. Electrons from valence band move to conduction band of P-type, and there you get the transfer of current. In that way, we are having P-type semiconductor and N-type semiconductor, and we are also having NPN junction diode. Those diodes we are going to study in physics, and this is the part of semiconductors. Next, we are having a part of insulators, which we all generally know. With the increase in temperature, the energy difference is so high. The energy difference is so high that with increase in temperature, the difference cannot be matched. That's why they continuously act as insulators like our wood. Okay. So in this way, the band theory works, where we will be having conduction band and valence band. These conduction band and valence bands are nothing but the valence electron shell and empty shell, which is present in the same subpart. Okay. So this is what valence band and conduction band part which we have seen. Next we will be having paramagnetic, diamagnetic and ferromagnetic compounds, and after covering this part, our chapter will be done for solid states. Now we are having diamagnetic, paramagnetic and ferromagnetic compounds. Diamagnetic compounds are those which have all paired electrons present in them. That's why they are known as what? Diamagnetic compounds. And when these diamagnetic compounds are placed under magnetic field, imagine this is the direction of the magnetic field. When I am trying to place that diamagnetic compound in the magnetic field, it will get repelled. Okay, it will get repelled in the magnetic field. Now if I am having paramagnetic compound will have one or more than one unpaired electrons. Okay, paramagnetic compound will have one or more than one unpaired electrons. If I will try to place that paramagnetic compound in magnetic field, when I will place paramagnetic compound in magnetic field, there will be increase in weight, or the weight will go on slightly increase, or there will be force of attraction between the magnetic field and the paramagnetic compound. Okay, in diamagnetic part gets repelled, paramagnetic part gets attracted. Now if we will go for ferromagnetic compounds have large number of unpaired electrons. Okay, and when they are placed in the magnetic field, they are highly magnetic, and we can make magnetic compounds from those ferromagnetic materials. Iron is generally known as ferromagnetic, where Fe has 4 unpaired electrons, and these 4 unpaired electrons are responsible for ferromagnetic nature of that ion. And when that ion is placed in the magnetic field, the magnetic field attracts that ion and the weight of that ion increases. Okay, so these are the parts of diamagnetic, paramagnetic and ferromagnetic compounds. These questions are asked for 1 mark, where you have to write down 2 points. So first point will be what? Total number of electrons, whether it is paired on or unpaired, and the second point will be for magnetic effect. In this way, try to make down the notes of the solid states, try to solve the examples, try to use the log table, and take good practice of the examples. Our solid states is done. We are going to see the second chapter, that is solution and colligative properties, and we'll start with it in the next lecture or next video. Thank you.